Now, just like with the previous math problems we've done, what I want you to do is compare what we do here with what you did. And if you got it all right, tell us that you got it all right. If you didn't, I want you to see if you can identify what you did wrong. Like, did you subtract the temperatures wrong, or did you misread something? And so that's where we're going to start here. Is I collected all of the measurements that were made in the video. And you know that you may get a slightly different answer depending on how you recorded the values. Like, did you actually get the high temperature of the water? We've got to read the graduated cylinder, and you and I might disagree just a little bit. Remember, it's okay if we're off just a little bit, but you've probably got to be pretty close to the number I say. Over here with the balance, you remember the balancer was flickering around, and I paused the video right here. Maybe you had an 8 there. That's okay. Those minor differences aren't a huge deal. And then for the temperature of the metal, we've got to remember to use this side over here. Okay, so I have my blue pen out because generally I always start with the water. Remember, that's where I usually start my work. So do we know the mass of the water? Well, yes we do, because we know the volume of the water, and I see the bottom of the meniscus right there, which looks like 41, 42, 43, 44. It's definitely between 44 and 45. I'm going to say 44.6. Okay? So 44.6. Now that's milliliters, but we know there's 1 gram per milliliter with water, so I'm going to say 44.6 grams. You might be wondering, could I have taken this water and weighed it on the balance? And the answer is yes, I could have. That probably would have been the more precise way to do it. Sometimes when you have a lot of water, the balance hits its maximum. But I think here we definitely could have done that. Okay, so we have the mass of the water. Remember, the specific heat of water we always know because we can look it up in tables. And this is not something you have to memorize. We'd always give you a table that had it in there. And now we need the change in temperature of water. Well, we do have the change in temperature because we have this, which is the initial temperature of the water, and we have the final temperature of the water. And you remember that change in temperature is always final minus initial. So if we want that, we have to do 34.7 degrees Celsius minus 23.0 degrees Celsius. Sorry about my phone dinging. And then we can do our math here to calculate Q. So we always start our work on the water side of things. So now I'm going to plug in my numbers. So I've got my mass in here, and that's a 44, not a 14. I've got my heat capacity of water, and the change in temperature was 11.7 when I subtracted those two. And I'm just making sure the sign makes sense. It's positive 11.7, which means the temperature went up. And it did. It was colder at the beginning. It went up. It makes sense that it's an increase of 11.7. All right, so when I multiply those three together, I get positive 2183. I'm going to round it to 3 right there. And remember, rounding is not a huge deal. If you stopped right here, that's fine. If you said 29, that's fine. No big deal. And that's joules of energy. Now let's stop and think about what this number means. That means from the water, did the water gain or lose that heat energy? Well, the positive sign, the fact that it didn't come out negative, tells us it definitely gained that heat energy. Which makes sense. And where did that heat come from? Well, it came from the metal. So when we go to the metal, we know, and let me pick a different color here. Though there's no gray, I guess I'll just go with black. We know that Q for the metal is negative 2183.3. We have to switch the sign here. And the negative means that the metal released that energy. And of course that makes sense. The heat was coming out of the metal, and so it's a negative sign. And it's going into the water. Okay, we have Q. Let's think of what these other things we need. Now, we're trying to find the heat capacity of this mystery metal. I'll put a little question mark there. Do we know the mass of the metal? Yes, we do. It was 93.19. What units? Grams, because it's a mass. The change in temperature is always final minus initial. Well, the initial temperature was 225. So we know that, 225, that's the initial. But what was the final temperature? Well, the final temperature is 34.7, and the reason is because the metal, which was at 225 degrees, was put in the water, and it was cooling down as it released its heat to the water, and it stopped at the point where the water quit warming up. Because think about it, if the metal was higher in temperature than 34 degrees, the water would warm up even more, right? But it stopped warming up because the metal was now at the same temperature. So that's 34.7. It's pretty darn cool that that this final temperature is the same on both sides, and that's one of the tricks to doing calorimetry. Okay, now if we want to solve for C here, all we have to do is do Q equals mc delta T, and we're going to plug in everything except for C. So I subtracted delta T, these two numbers, and because I subtract 34 from 225, I got negative 190, which means the temperature, the negative means the temperature went down, which it did, right? It went from 225 down to 34 degrees. It was going down. That should be negative. My heat was negative 2183, and there's my mass, which we recorded up here. Now all I have to do is solve for C. And remember, you got to get C by itself on this side of the equal sign, right? This whole side over here, you have to have just C. That's what I want. In order to do that, I've got to divide both sides by 93.19 grams, and I have to divide both sides by negative 190.3. That will cause that to cancel, and there we go. I've got my C by itself. And over here, I'll have my negative 190, because remember, I got to do it on both sides. And so then to solve it, all I've got to do is do negative 2183 divided by 93, hit enter, and then divide by negative 190, and I get 0.123. Well, that's kind of an interesting number. The unit's joules per gram degrees Celsius, because that's what a specific heat always is. So this is the specific heat of this mystery metal. All right, I wonder how we did. You guys probably are thinking, that is not a mystery metal. Any guesses what metal this is? Well, it turns out to be copper. And copper was one of the ones that we did at the beginning in the warm-up. And copper's specific heat is actually around 0.369. You could go back and look. I've forgotten what it is, but it's somewhere in there. So you can tell we're off by quite a bit. And I think the reason we're coming out low is because we're not using that styrofoam cup. But if we'd used that styrofoam cup and been really precise, if we hadn't had the problem of having to take the metal out of the oven and let it, lose a little heat to the air at first, I think we would have gotten this higher number. And if you're super careful, remember, you should get the exact same value, and then you can identify the metal. All right, now if you're looking at this and you got 0.124 or 0.120, you probably did it right. The only difference was we may have disagreed a little bit on the reading of the graduated cylinder and things like that. That's not what we're worried about. When you're looking at your work, you don't need to worry about that. But if you were off by quite a bit from this number, then I want you to look and make notes. What did you do differently? And sort of make reminders for yourself for next time. All right, that's the end of this lesson on how to use calorimetry to figure out the specific heat of a metal. What's coming up next, of course, is a little bit more practice. So go to that next assignment and try it out while this is fresh.